This video will go over section 8.8, which is on colligative properties. So colligative properties are properties of a solution that depend on the concentration of the solute, but not its identity. So it depends on the number of particles present in the solution, and it doesn't matter the type of the particles. So the number of dissolved solute particles affect the properties of the solution, but not the identity of the solute. The identity of the solute does not. And so the colligative properties we will look at are the elevation of the boiling point, the lowering of the melting point, and the pressure due to osmosis. So let's talk about the elevation of the boiling point first. So a non-volatile, so let's talk about a non-volatile solute. So a solute that would be volatile will give a lot of vapor pressure above liquid. And a solute that is non-volatile has a negligible vapor pressure at a given temperature. And so it will lower the vapor pressure of any solution it is put in. So think, for example, about a solid. Solids have very little vapor pressure compared to a liquid that gives off a lot of vapors like acetone or ethanol or isopropyl alcohol, like rubbing alcohol. These have a lot of vapor pressure, but a solute like salt or sugar or any kind of solid would be considered a non-volatile solute. So a non-volatile solute has a negligible vapor pressure at a given temperature, and so if you put it in a solution, it will lower the vapor pressure above that solution. And so this brings about the elevation of the boiling point for that solution. So a liquid solution that contains a non-volatile solute has a higher boiling point than the solvent alone. So you increase the boiling point when you add a non-volatile solute in a solvent. And it is well known for water what happens, how much the boiling point is elevated. And so 1 mole of any non-volatile solute particles raises the boiling point of 1 kilogram of water by this amount, 0.51 degrees Celsius. So we will only look at water as a solvent in this case. And so the normal boiling point of water is 100 degrees Celsius. And so if you have 1 mole of any non-volatile solute particles in there, or let's say, for example, 1 mole of salt or any kind of ionic compound, it will raise the boiling point of 1 kilogram of water by 0.51 degrees. So instead of being 100 degree, it will be 100 degree 0.51 degree Celsius if you have 1 mole of any non-volatile solute in 1 kilogram of water. So let's see how we can apply this knowledge by going through this learning check. So what is the boiling point of a solution that contains 2.0 moles of CaCl2 in 1 kilogram of water? So we have 1 kilogram of water, and we know its normal boiling point, it's 100 degrees Celsius. However, we know that there is 2 moles of CaCl2 in there, and we have to find out how much it will raise the boiling point of water. So 2 moles of CaCl2. CaCl2 is an ionic compound, right? We have calcium in there, which is a metal, and chlorine is a non-metal. So a metal and a non-metal make an ionic compound. And so CaCl2 is an ionic compound that, when placed in water, dissociates into ions. So we have to find out what are the ions that CaCl2 dissociates into, and especially how many ions it dissociates into, because this property of boiling point elevation depends on the number of particles, not the type. So we have 2 moles of CaCl2 in 1 kilogram of water, and when we dissociate CaCl2, it completely dissociates. It's a strong electrolyte, which means it completely dissociates into its ions. And Ca is a non-ion. It's the Ca2 plus ion because it's in group 2A and it's a metal, so it's going to be Ca2 plus. And then the chloride ion is also a predictable ion from group 7A. And so 7 minus 8, it's a -1 ion. So when CaCl2 is dissolved in water, it completely dissociates into 3 particles. 1 Ca2 plus and 2 Cl minus. Why 2 Cl minus? Because in the formula of CaCl2, the subscript 2 here applies to chlorine, and it says there is 2 chlorine for 1 calcium. So we have 1 calcium anion and 2 chloride ions. And that is justified because to cancel the 2 positive charges from the calcium, we need 2 chloride ions to have 2 negative charges. So we can write this dissociation equation that shows that when CaCl2 is placed in water, it dissociates into calcium 2 plus 2 Cl minus. So that means 3 particles per formula. So when you have actually 2 moles of CaCl2, it actually means that you have 6 moles of solute, because you take 2 moles of CaCl2, but one formula unit of CaCl2 gives 3 particles. So you multiply the 2 moles by 3 particles, and it's 6 moles of solute that actually are in solution. So then you take those 6 moles of solute and multiply by the change in the boiling point per kilogram of water. And so it's 0.51 degrees Celsius per mole of solute in 1 kilogram of water. So then you multiply by 6 moles because we have 6 moles of solute. And 6 times 0.51 is 3.06 degrees. And we will run to 2 sig figs here because 6.0 moles has 2 sig figs, and 0.51 degree also has 2 sig figs. And the 1 kilogram is an exact number here. So you will run to 3.1. Then finally, we are able to calculate the boiling point of this solution containing 2 moles of CaCl2. And so it's 1 kilogram of solution that contains 2 moles of CaCl2. And so the boiling point will be 100 plus 3.1 degrees Celsius. So the boiling point of this solution will be 103 degrees 0.1. Due to the fact that there is, those moles of CaCl2, which account for 6 moles of particles. So that illustrates the boiling point elevation. So among the colligative properties, there is also the freezing point depression. So here, depression, you want to read that as lowering, the fact that it's lowered. So the presence of a solute molecules makes it harder for solvent molecules to form an organized crystalline solid. Imagine that when liquid is becoming solid, it needs to get organized into a pattern because from liquid to a solid, you go from a random packing of molecules to an organized and with a pattern. And so particles have to be able to arrange themselves in that pattern. And if there is the presence of a solute molecule in that solvent, it will be hindering the progress of the arrangement and will make it harder for solvent molecules to arrange themselves. So this will lead to the change of the freezing point. It will lower it. You will need to go to lower temperatures to be able to get that crystalline solid. So this leads to the freezing point depression, and a liquid solution that contains a non-volatile solute has a lower freezing point than the solvent alone. You need to go at lower temperatures to succeed into making the pattern and regular arrangement of the particles than if you had the solvent alone. And so again, we will only focus on water as the solvent. And so 1 mole of any non-volatile solute lowers the freezing point of water by 1.86 degrees. So the freezing point of 1 kilogram of water. So water's normal freezing point is 0 degrees Celsius. And so if you have 1 kilogram of water, normally freezes at 0 degrees Celsius. But now let's say there is 1 mole of any non-volatile solute in there. This will lower the freezing point of from 0 degrees Celsius to negative 1.86 degrees, right? So you lower it, which means you go into the negative temperatures to finally be able to freeze that mixture. So let's go through this learning check to see how we can apply this knowledge. So what is the freezing point of 1 kilogram of a 5 molar solution of NaOH? Assume that the density of water is 1 kilogram per liter. So we have this solution made of 1 kilogram of 5 molar solution of NaOH. So it is assumed that water is the solvent. And so when you have 1 kilogram of water, you actually have 1 liter of water. That's what the density of 1 kilogram per liter means here. So we can take it as 1 liter of water. And a 5 molar solution of NaOH, molar here is synonymous to moles per liter. So that means you have 5 moles per liter of solution. And so because we have 1 liter, so we have 5 moles in that 1 kilogram. So a 5 molar solution of NaOH actually means that we have 5 moles of NaOH in 1 liter. And since the density of water says that we have 1 liter when we have 1 kilogram of water, then that means we have 5 moles of NaOH in 1 kilogram of solution, right? Because 1 kilogram equals 1 liter. So we have 5 moles in 1 kilogram of solution. And we know that 1 kilogram of water normally freezes at 0 degrees Celsius. But we also now know that having 5 moles of NaOH in there will lower the freezing point. So we need to find out how many particles 5 moles of NaOH actually correspond to. So NaOH is again an ionic compound because it's made of a metal, sodium, and the polyatomic ion OH-, the hydroxide ion. And so when NaOH is dissolving in water, it will dissociate into Na+, because Na, being an alkali metal from group 1A, makes the ion Na+. And then we have OH-, the polyatomic ion. So when NaOH is dissolved in water, it completely dissociates into two particles, Na plus and OH minus. So that means we will need to multiply the number of moles of NaOH by 2 because we have two particles per formula. So 5 moles of NaOH actually means 10 moles of solute because you do the 5 moles times 2 particles per formula. So we have 10 moles of solute in 1 liter or 1 kilogram of solution. So then you take this into account and multiply the 10 moles by the change in temperature. And here the change in temperature is 1.86 degree. It's lowered, so that's why we have the negative sign here. So 10 moles of solute multiplied by negative 1.86 degree per mole of solute and per kilogram of aqueous solution, right? Remember that's the amount that 1 mole of solute in 1 kilogram of water that would be lowering the freezing point. So we multiply by 10 moles because we have actually 10 moles of solute. And so that's negative 18.6 degrees Celsius that we will lower the freezing point. So that means 1 kilogram of 5 molar NaOH solution has a freezing point of negative 18.6 degrees Celsius because you start from 0 degrees Celsius, the normal freezing point of pure water, and lower it by negative 18.6 degrees due to the 5 molar NaOH that is in there. And so that illustrates the freezing point depression.